Our next section is on simple harmonic motion. So the objectives will be, I will be able to understand the concepts involved with simple harmonic motion. We'll write notes from a video, discuss with peers, and work on sample problems in groups. Woohoo! Periodic motion. Simple periodic motion is that motion in which a body moves back and forth over a fixed path in a regular, constant fashion. The simplest example is an object bouncing on a string. So if you notice, we have F equals 1 over t, and this is the amplitude. The t is the period, which is the time for one complete oscillation. Frequency is the number of oscillations per second. Our first example shows our equation. The suspended mass makes 30 complete oscillations in 15 seconds. What is the period and frequency of the motion? So to find period, we go time over the number of cycles or oscillations. So we had 15 seconds over 30 cycles, 0.5 seconds, so our period is 0.5 seconds. So all we do is we put F equals 1 over t, so frequency equals 2 hertz. So simple harmonic motion, or SHM. In this type of motion, there must be a restoring force that causes the motion to repeat over and over again. In this case, gravity pulls the object down, while the spring is the restoring force pulling it back up. A restoring force, F, acts in the direction opposite the displacement of the oscillating body. Hooke's law. When a spring is stretched, there is a restoring force that is proportional to the displacement. So please note that we have F equals negative kx, where negative k is the spring constant. So if we need to find k, k equals F times the change of x. So the work done in stretching a spring. Work done on the spring is positive. Work by a spring is negative. So by pushing down, we're going in the positive motion, but as the spring pushes up, that's in the negative direction. Okay, so to stretch spring from x1 to x2, work is shown here, 1/2 kx squared minus 1/2 kx squared. Okay? So here's example 2, using Hooke's law. A 4 kilogram mass suspended from a spring produces a displacement of 20 centimeters. What is the spring constant? So the stretching force is the weight. So the weight equals mg of the 4 kilogram mass. So we have to do 4 times 9.8. So there is our weight. So equals W. Now from Hooke's law, we get our spring constant. So we have 39.2, which is our weight, divided by the displacement. Notice we changed centimeters to meters, and we get 196 newtons per meter. So we continue on with this. So we get 1/2 kx squared, the final minus the initial. Work equals 1/2 kx squared. We have the 196, what is the, because we're asking for the potential energy, and 0.08 meters squared. So we end up with this as the potential energy. So displacement in subharmonic motion is positive when there's positions to the right of the equilibrium position and negative when located to the left. Maximum displacement is called the amplitude. Velocity in simple harmonic motion is positive when moving to the right and negative when moving to the left. It is 0 at the endpoints and a maximum at the midpoint in either direction. Acceleration in simple harmonic motion is the direction of the restoring force. A is positive when x is negative, and negative when x is positive. Acceleration is a maximum at the endpoints, and it is 0 at the center of oscillation. So acceleration versus displacement. Given the spring constant, the displacement, and the mass, the acceleration can be found from right here, these two equations. Please copy them down. Alright, so acceleration is always opposite to displacement. So a 2 kilogram mass hangs at the end of a spring whose constant is k equals 400 newtons per meter. The mass is placed at a distance of 12 centimeters and released. So if you notice, we have the spring constant negative 400. We have x, which is the displacement of 0.07 meters, which has changed from centimeters, and we have the amount of mass, which gives us the acceleration. Example 4, we have acceleration equals the negative spring constant times a, which is 12 centimeters, and we have the mass again. So the maximum acceleration is here. So conservation of energy, for any 2 points A and B we may write, so whatever you start with you have to end with. It's the same thing that we've done before. So energy of a vibrating system, at points A and B the velocity is 0 and the acceleration is a maximum. The total energy is the potential plus the kinetic equals 1/2 k A squared. X equals positive, negative A, and V equals 0. Okay, so this is a little bit of review because we are doing conservation of energy. Okay, go ahead and take down these equations. So here we are using this. So a 2 kilogram mass hangs at the end of a spring whose constant is K equals 800 newtons per meter. The mass is displaced a distance of 10 centimeters and released. What is the velocity at the instant displacement x equals plus 6 centimeters? Okay, so again at this point we're just filling in the equations that we're using if we're looking for velocity. So we have a squared minus x squared. A is the mass displacement. Alright, and continuing on with the example, still looking for maximum velocity. Velocity is positive negative 2 meters per second. So the period and frequency is a function of mass and spring constant for a vibrating body with elastic restoring force. We're still using the same one. So F equals 1/2 pi with K over M, which is the spring constant. And then we have the period, which is 2 pi times the mass over the spring constant. So here's an example of that. Please notice where they put the numbers in.
From the back director, David Fredis. All Jefferson Silver students who are interested in trying out for the 2016-2017 Silver Fox Drum Line.
So here we have the simple pendulum. The period of a simple pendulum is given by T equals 2 pi L over G. For small angles, the frequency equals 1/2 pi G over L. And again, we have an example. Alright, that's it. That's a lot of work, so get these down carefully so we can go over them.